All right. Okay, the first one was condition right there, first thing, the equilibrium of two forces. Equilibrium of two forces. Let's see there are only two forces acting on a body. So then what is the conditions for equilibrium of those two forces? So if there's a body like this, let's say, if a one force is applied on the equilibrium, that's the resultant to be zero. The other force should be opposite to this, and also their magnitude should be equal to this, right? And to become the moment is zero, then another condition should be satisfied. Those two forces should be acting on the same line of action. No, this is F1. So this should be, if body is under the equilibrium, you can say this F1 should equal to F2, and their direction should be opposite to each other, and those two forces should be in collinear. Okay, let's write under this. The following conditions to be satisfied, following conditions to be satisfied. So P and Q, following conditions to be satisfied for the equilibrium of two forces, for the equilibrium of a body under two forces, for the equilibrium of a body under two forces. Okay, then you can write first one is the two forces should be collinear. Two forces should be collinear. Second one, magnitude of two forces, should be equal. Should be equal. Third one, okay, we are discussed about this equilibrium of two forces, right? So if a body is in equilibrium under two forces, then these conditions to be satisfied. First one is two forces should be collinear. Second one is the magnitude of two forces should be equal. The magnitude should be equal, and two forces should be acting in opposite direction. And the two forces should act in opposite direction. The directions. These three conditions should be satisfied. This is important that if these two are satisfied, we can't say it's an equilibrium. That's only that the must also consider, because in the case of this, if the force couple is applied, let's say this in this case that's equal and opposite, but not in the same line. So it's a collinear. So there's a moment then. So in this case only, when they are acting on the same line, or line of action is same, then only we can say here the resultant is equals to 0 and the moment about any point that is equals to 0. The G represent moment of torque, let's say torque, which is also 0. We can say then the body is under equilibrium. Copy down. Here you need to write this P equals Q, and the direction of P opposite to the direction of Q. In the second one, right? Equilibrium of three forces. Equilibrium of three forces. In this case, we can consider this two cases, right? The first case is when the three forces are in parallel to each other. When we consider about the parallel process, and let's write part A under this. When the three forces are parallel, when three forces are parallel, three parallel forces. Then what should happen? Parallel means let's say the object is like this. It's two forces acting in one direction, and another was the it's a parallel process. So this is P, this is Q, and this is R. Less. And here the condition two should be parallel and coplanar. So these two forces should be in the same plane. And the algebraic sum of these two forces in their direction should be equal to 0. And the moments of the three forces about any point should be equal to be 0. Right? And also we can say that vector sum of two forces, that's equals to the third one. If the sum of these two, this should be equals to this one to be equilibrium. And also line of action of these two forces should be acting on this line. It not be equilibrium. Okay, you need to write these conditions. You can write under this one. The three forces should be parallel and coplanar. The three forces should be, because these parallel forces we consider here, it should be coplanar. Three forces should be parallel and coplanar. That's first condition. And second, right, the algebraic sum of three forces, the algebraic sum of three forces in their direction algebraic sum of three forces in their direction should be 0. Should be 0. And then write the third condition. The algebraic sum of the moments. The algebraic sum of the moments of the three forces about any point. Three forces about any point in their plane. The point in their plane should be 0. Okay, according to this, I can say this. I will consider this point is A and this is B and this is C, and the distance between these two I'm considering X. Right. Sorry. I'll take the point P here, and distance between this P and different letter I will use, that is C and D here. P and T, that's a distance is X I'm considering. And this distance are taken as Y. Distance to R from this T is taken as Z. And this is the object, the force three forces acting on it. According to these conditions, the first, second condition we can write like so. If you consider all the forces acting upward, so P plus R, the minus Q, that's equal to 0. And this going into the second condition. So we can say there's the P plus R here, that's equal to Q. So that means that's the sum of algebraic sum of two forces should equal to other force. Three force system, that's 2 should be equal to the other one. And then this first condition, the second condition, taking the moment about the point D, right? That's equal to 0 because of the equal break. So the moment taken by this side, by this P cos P into X plus Q into Y. R give the moment to the other side. So it's the minus negative R to the Z. That's the way you are right. So that means clockwise moment is equals to the anti-clockwise moment. Right? Px, Qy, let's figure out. So it implies you that sum of clockwise moments that's equals to the sum of anti-clockwise. Sum of anticlockwise moment. So actually, this is the moment principle for a equilibrium. The object under equilibrium, the moment principle you can use like this. Because there are no resultant force. So resultant force is zero, then the algebraic sum of the moments of the individual forces in the system should be equal to zero. And draw and write and tell me. Hi. You finish right? Let me know. Sum of the clockwise moment that's equal sum of the anti-clockwise moment. Okay, I'll erase this one, right? In a parallel, non-parallel process, either part B, when three processes are not parallel or not parallel. So then you cannot draw the diagram like this. So we need to draw that's the first condition to be satisfied in the T process. Those three processes should be coplanar, company. They should be the same plane. Yeah, this is just like this. If the object is there, let's consider. The one process applied to this direction, another is another. At least these forces should be acting the same plane. And if it is in equilibrium, actually, this all three forces, their line of action should be intersected at one point also. If the force is going like this, two posts intersected, then other one will not, the line of action is not passing through this one. So we cannot say it is in equilibrium, right? Okay. Then condition wise we are right then. Condition right, just to draw this diagram and then write. Okay. Mark it as P, Q, and R. And also when you draw this, mark You can draw this all are intersected one point, right? So all are intersected at one point. You can draw like this. Okay, right? The first condition, right? The three forces should be coupler, na? Three forces should be coupler, na? And second, the lines of action should be meet at a point. The lines of action should be meet at a point. Should meet at a point here. Then. Should meet at a point. Third one. If this is in equilibrium, if you can remember that's in the vector, you use that vector triangle rule to get the sum of these three forces. So right, draw the P is this way, and then the Q is this way, and then the R is you are drawing like this. So these three forces can be represented in a cross triangle. So we call this a force triangle. Right, let's say BC, let's say. So that is the force P, and force Q, and force R. We can represent these three forces as their magnitudes and direction in a closed triangle. So then that should also be satisfied. If not, it is not equilibrium. That's why these two equals to this one. So then they cancel out and resultant becomes zero. Okay, then that is the third condition. The three forces should be able to be represented. Three forces should be able to be represented by three sides of a triangle. By three sides of a triangle. Three sides of a triangle taken in order. Taken in order. Taken in order. Okay. You can draw this and also this one. And here then you can write this AB the vector plus BC vector plus CA vector. That should equal 0. Should equal that's AB plus BC, that's equal to AC, and AC plus CA, that is minus CC, so then cancel, so it becomes 0. And not only that, if it's in this kind of case, we can apply the Lame's theorem. But that Lami's theorem is not in a syllabus. But we can say that this force divided by the sine value of the angle between the other two forces. And this force divided by the sine angle of these two forces. And this force divided by the sine angle of this must be equals to each other. I'll show you later. So just write this then. Write this one also. Draw this one. When you're drawing this, don't draw the triangle as you want. Just here, let's see this P and P is parallel. It's Q and Q are parallel, and R are parallel. We're drawing this triangle according to these forces, the representing their direction and magnitudes in the same way. Okay. Then write there. After that, you can write in. When an object is an equilibrium, when an object is in equilibrium, when an object is equilibrium, under three non-parallel forces, under three non-parallel forces, three non-parallel forces, it obeys, it obeys triangle law of forces, triangle law of forces. Then write triangle law of forces, triangle law of forces. Now that right? If an object is under equilibrium, the object is on equilibrium under, sorry. If an object is in equilibrium, if an object is in equilibrium under three concurrent coplanar forces, three concurrent coplanar forces then they can be represented in magnitude and direction. They can be represented in magnitude and direction by the sides of a triangle, taken in order. Taken in order. You can write under this as a note. You can write as a note. Under this situation, the Lami's theorem can also be applied. This, I'll do it as a note, right? It's Lami's theorem. Under this condition, the Lami's theorem can be applied. This Lami's theorem means I only write those. Forces only mark. P, Q, and R, let's say. This angle will be alpha, beta, gamma. Okay, this not under the Lami's theorem, you can write there. You don't need to mention the theorem, but you can apply this anyway, right? Right? If a body is in equilibrium under three coplanar concurrent forces, if a body is in equilibrium under three coplanar concurrent forces, then each force is proportional to sine of the angle. Then each force is proportional to sine of the angle between remaining two forces. So we can write like this: sine of the angle between remaining two forces. According to this theory, you can write this P, Q, R, the three forces, that the angle between the Q and R is alpha, P and R is beta, P and Q is gamma. So then P divided by the angle between the other two forces alpha, so sine alpha, and Q divided by the sine beta. And because why we are writing is this is P proportional to the sine alpha. Let's say it is a constant type sine alpha. The Q proportion that constant time sine beta. So that means the P to sine alpha, Q to sine beta, R to sine gamma, it's a constant. So it's the same constant for the given system. You can write it. right? Okay, then we know that when the body is equilibrium under two forces, it should be equal and opposite and in the same line. And if non-parallel, parallel three forces, with that we know that all r should be in the same plane, and resultant force should be 0, and the moment taken by one point in the plane should equal 0. And non-parallel forces, so you can draw it in the as they meet in the same line, same point, and also there's a that can be represented in the cross triangle. Right? Then if more than three forces, it's many forces, any number of forces, then you can represent it in a polygon, cross polygon. Right? And write the third one. By the third conditions that right the equilibrium of any number of coplanar forces. Equilibrium of any number of coplanar forces. Right. That's the conditions to be satisfied is right under that the following conditions to be satisfied. Following conditions to be satisfied for the equilibrium of any number of coplanar forces. For the equilibrium of any number of coplanar forces. That's the first condition, right? Many forces acting like this, the concurrent. Right. You're considering the result. Remember how we get the resultant of this Rx component. You can algebraic sum of all the resolve. You can resolve this in x direction and take the algebraic sum of those. And in y direction, you can reduce it to the single one, take the resolve in y direction and take the algebraic sum of all. And then the resultant is r square plus ry square. The square root of this. So it's under equilibrium, r should be 0. So when the r is 0, both rx and ry should be equal to 0, not only one. So this should be equal to 0 and this should be equal to 0. So it means you that if you resolve these forces to any direction, right, the algebraic sum should equal to 0. And also taken the moment about any point, that's also equals to 0. Algebraic sum of all the moments given by all the forces in this system, that's also equals to 0. Okay. That is the three conditions. Three conditions if one direction, if you consider that the resultant is 0, perpendicular that direction is that's also that algebraic sum should equal to 0. First one right then. First one right. The algebraic sum of the components. The algebraic sum of the components of all the forces algebraic sum of the components of all the forces in any direction should be 0. In any direction should be 0. any direction should be 0. And the second condition, right? Second condition, right? The algebraic sum of the components of all the forces, the algebraic sum of the components of all the forces in a direction perpendicular to the above mentioned, in the direction perpendicular to the above mentioned direction, should also be 0. Should also be 0. Okay, the third condition. Third condition, right? The algebraic sum of the moments of all the forces. The algebraic sum of the moments of all the forces about any point in their plane, about any point in their plane should be 0. Should be 0. I'll show it as a body. Right. Let's say we having the body like this, the object have so the forces acting, let's say on the body like this. Point O I'm consider here. Forces like the P, Q, or it's let's say perpendicular distances. Those two forces. This one I'm considering. मैं हरो लगाना दिक्कत तो आ गई million. Make P or secretary the distance I can consider it as while taking this so we need to get the distances also. You can consider it as x. It's better than, right? This distance, the p equal to the amount of the p. This is a point O here, and distance to the force p, perpendicular distance, that's say x, and to the force q, that's perpendicular this y, and to the force r, I can do this distance as z. Is it clear for you? And force S, perpendicular distance is number A. And also this angles and consider, right? This is horizontal. And the force P with the horizontal, it's make an angle alpha, let's say. Alpha. And this force Q make an angle. This is beta. And this suppose S. I'll draw some here. Let's say gamma. This angles all like angles are marked with horizontal, right? So then according to this, these conditions we satisfy under the equilibrium. Okay. If the body is in equilibrium, body is in equilibrium, all the components, the sum of the component to this direction, that is this one minus P cos alpha, and this one plus P cos beta plus Q cos beta, and R is the same one, and this one minus S sine, sorry, cos gamma, actually equals to 0. And upward, that means the vertical plane that's perpendicular to the, this is in x direction, this is in y direction. And P as a plus P sine alpha plus Q sine beta. This R will not come, it's 0, and minus this sine gamma. That's also equal to 0. And taking the moment about O should equals to 0 also. Right? This P gives the moment not to the clockwise, it's anti-clockwise. So anti-clockwise direction, this moment is equals to P into X. The perpendicular to P is X. And Q's, this minus side because anti-clockwise, the Q multiplied by the Y, and the R multiplied by, because it gives a clockwise moment is Z, and it gives the moment to the other side, it's multiplied by simple A. This also should equal to 0. Okay, you can copy it down and write these are the conditions. And you can write the equation like this for equilibrium system. Then you can solve for the unknown load. And also we can represent this in a polygon. හරිද? Right? Then you can write, put a sign right there. The principle of moment. The principle of moment. The principle of moment. For a equilibrium system. For a equilibrium system can be stated as below. As below. As below, right? So that is the moment, the algebraic sum of the clockwise moments, and that's equals to the algebraic sum of the anti-clockwise, right? You can write there. Then write there. When a body is in equilibrium, the total clockwise moments about a point, total clockwise moments about the point, total clockwise moment about the point equals the total anti-clockwise moment about the same point, equals total anti-clockwise moment about the same point. Then also write there, right? Just as, gonna put a star in, right? Just as three forces in equilibrium can be represented, just as the three forces in equilibrium can be represented can be represented by a triangle of forces. By a triangle of forces. A large number of coplanar forces in equilibrium can be represented by a polygon of forces. By a polygon of forces. This can be represented. The Q is this direction, so you can starting from, let's say starting from P. P is in this direction. First you draw the P pose, right? Which is AB. And then Q is the other. You can draw this parallel to the Q. This is P and this is Q. See, let's see. And R, you can draw the line parallel to the R. And the magnitude should proportional to this. See D lines. Yeah, quarter times. And S should parallel with S like this. So this is the E line. And then T is cross the polygon with the T. Right. So then it is equal. So you can say that's AB plus BC plus CD plus DE plus EA. That should equal to C. Because you know that in order you are drawing this AB plus BC, that is AC. AC plus CD, that is AD. AD plus DE, that is AE. AE plus EH 0, because EA means is minus AB. Okay, draw this. Okay. Then consider we have a body like this. I can place this body in equilibrium in this way. And also, maybe that I balance you can balance it like this also. And also we can place it in this small tube. The same body, the three orientations. in equilibrium. But if you apply small slight displacement to there, to tightly tilt it, so what happens? So it's more tightly, that's the word tilt color. So there's center of gravity somewhere here. Right. So that tilt curve may be there. Center of gravity moment is anti-clockwise direction, tilt direction not opposite. So then this center of gravity, the weights, its weights will bring that body to the previous place back. Right. So it will not fall down. So it comes to the same position. Then we equilibrium at the same position. So that kind of equilibrium we can consider it is stable then. But in this case, if you apply slight displacement, it fall down. It means that the equilibrium never come to the origin place, the initial equilibrium state. And this case, if you apply slight displacement, this will small travel, and then the different position they make the equilibrium same as the previous. So such equilibrium is neutral. So there are then many different states of the equilibrium, right? We can make a object equilibrium in many ways. So those are mainly we can identify as three ways. So this is called the stable equilibrium, in this mode we call the unstable equilibrium, and this is the neutral equilibrium, right? And also another condition, another state we can call that the limiting equilibrium. That means the equilibrium will be limited to a one place. Let's discuss it later. First to write there states of equilibrium. Write the topic, the state of equilibrium. State of equilibrium. Then write, yeah. There could be many ways. There could be many ways in which a body can be placed in equilibrium. In which the body can be placed in equilibrium. Right. These are called state of equilibrium, of which one would be, these are called states of equilibrium, of which one would be, of which one would be safe, another moderately safe, one would be safe, another moderately safe, and yet another unsafe, yet another unsafe. In the three main states of equilibrium are, the three main states of equilibrium are First one, right? That's stable equilibrium. Second one, right? Unstable equilibrium. Third one, right? Neutral equilibrium. The EQM, that's equilibrium, right? First, right is stable equilibrium. First, right, and the stable equilibrium. Right, the first one, right? Stable equilibrium. Under that, right? When a particle is displaced slightly, when a particle is displaced slightly from its initial position, from its initial position, from its initial position, the force acting on it, the force acting on it, bring particle back to initial position, bring particle back to initial position. It is called stable equilibrium. It is called stable equilibrium. Then there is the second one, unstable equilibrium. Unstable equilibrium. When a particle is displaced slightly from its initial position, when a particle is displaced slightly from its initial position, the force acting on it, the force acting on it tries, force acting on it tries, it try, it tries to displace the particle further, to displace the particle, to displace the particle further, further away from initial position, further away from initial position. It is called unstable equilibrium. It is called unstable Okay, sorry children, I had a call. So then write the neutral equilibrium. I will draw these separate examples that someone write. Lines supposed to write down. The neutral equilibrium, when a particle is slightly displaced from its initial position, when a particle is slightly displaced from its initial position, the force initial position, if it continues, to be in equilibrium, if it continues to be in the displaced position, if it continues to be in displaced position, to be in the displaced position, it's said to be in neutral equilibrium. It's said to be in neutral equilibrium. Okay. Then we can draw like this. If we consider a ball at the bottom of a ball, right? It's like this. This is a ball. The ball is at the bottom of that. If you slide this, when slide displacement is going up and then come back to there, the position, this initial position, it will be gain equilibrium, makes equilibrium, right? So this is stable. And if you have the ball in this position, right? Like this. I face the body, the particle there. That is in equilibrium in this case. But if side displacement is given, it's move away from that point. It never come back to this position to be equilibrium. So it's unstable. If you place the particle this position, if we given a slight displacement, what happens? It goes to the another place and it continues its equilibrium at that new place. So that is neutral. In these cases, you can see that this case and this case, this is that's the center of gravity is much above. The center of gravity is close to the line surface. So we can say then normally in stable equilibrium, center of gravity to be equal. If you want to make the object in stable equilibrium, you need to design it as the center of gravity come much lower, right? The vehicles also making in that scenario. The center of gravity is much below, that's much closer to the ground. Thus, this three-wheelers are unsafe and motorcycles are unsafe than the other vehicles. Because their center of gravity is much above, right? අනිත් එක තමයි ගොඩක් දැන් ලෝරි three wheelers හදලා තියෙන ඉක්විලිබ්‍රියම් එක ගන්න තියෙන්නේ පොඩ්ඩක් එහෙම ඇලුනාට එකපාර පෙරලෙන්නේ නැති වෙනවා. කාල ඉක්විලිබ්‍රියම් එක ස්ටේබල් ඉක්විලිබ්‍රියම් කරේ. අපි මොකද කරන්නේ ওই වාහන ගෙනල්ලා ඕකට තිතේ තියෙන ඇලෝ වීල්ස් වලින් පුළුවන් තරම් ඒවා ගහනවා. ඕන හූ ට්‍රැක් එකක් ගහනවා අරව ගහනවා මේවා ගහනවා වටේම තියෙන අකඩේ වෙල්ලලා අර ස්ටේබල් ඉක්විලිබ්‍රියම් සෙන්ටර් ඔෆ් ග්‍රැවිටි එක පොඩ්ඩක් වෙනස් කරන එක පොඩ්ඩක් උඩට ගන්න. ඊට පස්සේ පොඩ්ඩක් කානුවක් හරි ගලක් උඩින් හරි ගිය ගමන් මොකද වෙන්නේ? මේ බංගාල පෙරලෙන්නේ. ඒක තමයි මෙහි කරලා තියෙන්නේ. හරි. මේ වාහන හදලා එවන්නේ ඉක්විලිබ්‍රියම් එකේ තියාගන්න පුළුවන් වෙන විදියට හොඳට. මේක මොකද කරන්නේ? ගෙනල්ලා ඔක මොඩිෆයි කරලා එක එක ඒවා කරලා අන්තිමට කොහම හරි සෙන්ටර් ඔෆ් ග්‍රැවිටි එක තිබ්බට වඩා එක උඩකට හරි කොහෙට හරි අන්ස්ටේබල් කර ගන්නවා නිකන්. මේ ටික ඇඳගන්න. මම මේ තව කීපයක් අඳින්න. If you consider about the bottle, Local also we can make an equilibrium like this table. Right. And we can make an equilibrium in this mode also. එකම බෝතලේ make this is an equilibrium in this mode also. මේක ඉඩ තියෙන හින්දා consider the object like this. මේ දෙකක් අදින්න නිකන් පේන්න. Two objects මේක ඇඳලා පෙන්නන. හරි. Both sides different bodies. අපිට මෙහෙම තව එකක් දැන් you hang a body like at this point. This is the center of gravity. If the center of gravity is just below, since below the going to hang the body, so it is in equilibrium, so it's stable equilibrium. Make it a slide this way, make a and also the body can be pivoted to point below the center of gravity. Yeah, the pivoting point is this point now. Now it's pivot point. Center of gravity is now above. Nearby चालू आती है मैं कैरकिला आनी पड़ता है. Stable position negative ना कैरकिला. और it's unstable. Make it नहीं center of gravity is there. Unstable. If you pivot the body at the center of gravity, G and X are same. This is unstable. This is neutral. here. So take a center of gravity. Slide this person. ඔය වතයි කර ගිනේ නෑ. ඒ දාගන්න here there's x and g. I marked the x is the pivoting point. G is the center of gravity. Here the center of gravity and the pivoting point same. If you finish the drawing, let me know, right? I don't know that. Finish or not? Please raise your hand. Oh, you can write it says. All right. Then out of this, you can see this is most unstable. That's unsafe position, right? Most unsafe. So these two are little bit safe. This moderately safe and this is uh, safer. Please try and write there. Out of these three states of equilibrium, out of these three states of equilibrium, it can be seen that the unstable equilibrium position is the most unsafe position. Most unsafe position. And also in these cases, you can see, you notice it there. So I'll draw it again. Another one that's in this case. So there, yeah. And this and this, right? Make a basic. And here the center of gravity is somewhere high. The center of gravity is not changed with this position. You can see in this case, center of gravity is lowest at this point, and it's topper, and it's a moderating. So that center of gravity is much below means this potential energy is also, we can discuss the potential energy later. This potential energy is of minimum. The potential energy is, because potential energy you already know that is mgh. No? So from this level, we draw that h is higher there, it's lower. So it's, so then we can say that if the object having higher potential energy is unstable. As an example, I tell you. And let's see, it is you, right? This you mostly like to be in standing up or in sleeping mode. Sleep. That's why in this case the center of gravity is much above. So it's unstable. That's a potential. So always you like to be sleep. Right? So then this is not stable because lesser potential energy make you stable. The electrons are also, you know, there's electrons and the atoms, anyone. They don't like to be in upper, that's high energy states. They always tries to release the energy and comes to the lower energy levels. Right? So that's also because if I is unstable. So they like to release the energy and then come down to lower states to be stable. So that's come from the electron. So then it's not the matter of you. If you feel sleep, you always, that means it's not matter of you. So because you are in high energy state, so you need to release it. That's why you tries to come to the sleeping mode. It's okay. Right. The right there, which is right. It can also be seen that the lower the position of the center of gravity, lower the position of the center of gravity, lower the position of the center of gravity of a body, the more stable or safe the body is. The more stable or safe the body is. Save the bodies. Okay, give me a minute, please. Power cut. Kaparak power gear. I don't know. Okay, can you see the button? Okay. සිතට ගෙනයාගන්න. එක පොඩි එක lower තියෙනවනේ තමයි. The actual thing is for the stable equilibrium or the equilibrium cases is depends on the potential energy processed by it, right? So you can write there the potential energy ගැන පස්සේ වෙන විස්තර කරනවා. එතෙන්දී නිකන් mention කරනවා. The potential energy possessed potential energy possessed by an object is the main factor of its states of the equilibrium. Its states of the equilibrium. Right, the if an object has low potential energy, an object has a lowest potential energy, an object has lowest potential energy, it is the most stable position. Is the most stable position. And its highest and its position of higher potential energy is more unstable. ඒකට ඔයාලට දැන් මොකක් හරි තීරණය කරන්න දුන්නොත් question එකක් select the most stable state එක නැත්නම් unstable state එක කියලා you need to select as you have to check that where the center of gravity is lower or where the center of gravity is high. If you apply the force just below the center of gravity, that's below the center of gravity, right? So it is easy to make a translational motion above the center of gravity, so it tends to roll down, so it's into rotational motion. So also keep in mind. Okay, we'll discuss some questions related to this, because it theoretically about the equilibrium is over. We have to discuss about the limiting equilibrium one also, but before that we need to discuss some questions related to this. Write some example, write an example. Write an example. I will draw the diagram there. A ladder is placed on a smooth floor. Example, first example, a ladder is placed on a smooth floor, and held against a rough vertical wall, right? Is ladder remains in its position? This question, right? You need to explain this. Is ladder remains in its position? Ladder the question given, this is smooth and this rough. You have to mark the forces acting on it and then explain this, right? This is the question. And then write a second question. Write a second question. $500 grams of, right? 500 grams of object, that's a body. 500 grams of body is hung at a fixed point by massless inextensible string. Is hung at a fixed point by a massless inextensible string. Okay, the string is pulled. The string is pulled back. The string is pulled back as it makes an angle 60 degrees with horizontal. The string is pulled back by a force F. Right. The string is pulled back by a force capital F. Pulled back by a force capital S F. As the string makes an angle 60 degrees with horizontal. Find the value of the pos f. මෙහෙම වෙයි කියන්නේ හරි. මෙහෙම තිබ්බ එක මේ pos එකේ මෙහෙ රදින්න. You pull it back. So then it's become like this. This is 600. Pull back. This one. The third question, I'll give the 2-3 questions and then we discuss. Third question, right? A smooth sphere of radius simple r. A smooth sphere of radius simple r. Radius simple r. And weight w. And weight w. Hung by a string. Hung by a light string of length simple r. Of length simple r. So just like this. Length is simple and this radius is simple. Okay. Then write one end of the string is fastened. One end of the string is fastened to a point on the surface of a sphere. To a point on the surface of the sphere, while its other end is fixed to a point on a smooth vertical wall. Points on a smooth vertical wall. Determine the reaction of the wall and the tension in the string. Determine the reaction of the wall and the tension in the string. Okay. Let's try to do this. Current boundary. හරිද? එතකොට how first you need to mark all the forces acting on it. So the normal reaction in this normal reaction is, let's say, R1 and this R2, and the weight of the ladder is down. So it has a tendency to move this direction. This rough surface has also force upward. That's friction. According to this figure, you can see there's a force. The normal vertical plane, this upward force are there, also downward force is there. So there may be the balance thing, right? But the forces acting on this ladder horizontally. There's only one single force is there. To make it equilibrium, at least there should be the two forces, right? So if one force is there, so the one should be opposite to that here. So then there's no any other forces opposite to act. So that means the ladder cannot be keep in this position then. So it slides now. You need to write it then. You can draw this Peabody diagram and then write there. According to the Peabody diagram of the ladder, according to the Peabody diagram of the ladder, the R2 horizontal force, right? The R2 will not be balanced by other forces. Or you can write there are no other forces to balance the R2. There are no any other forces to balance the R2. Therefore, the horizontal forces are not balanced. The horizontal forces are not balanced. So the ladder cannot be in equilibrium. The ladder cannot be in equilibrium in its position. In this position. Right? I explain this, right? And in here, tension applies. And the force F applied there. And weight is 500 gram. So 0.5 kilogram means that's 5 Newton, right? 5 Newton. Weight. So this is 90 degrees, right? So we can draw the triangle corresponding to this. And this F is there. Force F with the 60 degree with the horizontal. This force tension is. And then this 5 Newton vertically down. This tension. This 5 Newton. This is in equilibrium, right? This 60 degrees. So using this triangle, you can write this tan 60. That's equals to the 5 divided by F. So tan 60 equals to the root 3. Then you can write F equals 5 divided by root 3. If you want to find the tension, it's you can write as, so I'll write it here. The sine 60. Sine 60 is 5 over t. The tension then equals to the 5 divided by sine 60. Sine 60 root 3 over 2 actually. So then it is 5 multiplied by 2 divided by root 3. So 2 into the 10 over root 3. That's the tension. This is the force applied. This is in general method I'm doing. The Lamis theorem also you can apply. That's how can I This is 120 degree. So this is 90 degrees. So you can write in that's t divided by 90 sine 90. So that's 5 divided by sine 120 and f divided by this angle is 150. So by equating this, you can this is sine 90 is 1. So then t equals 5 over sine 120. Sine 120 is root 3 over 3. Let's take 2 t graphs and 10 over root 3. This one. And by equating these two, this half cancel, then f equals 5 over root 3. This is easy, you can write. You can simplify and give the answer. Okay. And here, forces still mark and the mg, the weight is given as w here. A normal reaction is passes through this center of the sphere. This is perpendicular to the R. This normal reaction capital R. And then its strength should be attached to the R because in equilibrium, these three forces only this sphere is in under the equilibrium, only three forces acting. The one is a string, that's a tension of the string, normal reaction of this, and the weight. If we draw these 3 points, you can write like this. Line of actions you can draw like this normal reaction, that's tension. And this distance is R. This is also R. R, 2R. So this angle, let's say theta. So you can write sine theta. That's equals to this R divided by, from here to this hypotenuse is 2R. So then sine theta is half. And theta is 30 degrees. Then if this is 30 degrees, so this angle is 60 degrees. So you can make it similar to this thing. Right? That's similar to this. So we can write in drawing this triangle, you can write. If you are not familiar with this drawing the triangle, then you can resolve this upward forces, right? Let t sine 60, that's equals to the downward force, that is W. There are no others. Then t equals sine 60 root 3 over 2, that's 2W over root. And take the horizontal. Because R equals R only this side, there are t cos c. T cos 60 is the other one. So then R you can write. Yes. T is 2W over 2. 2W over root 3. And cos 60 is half. The two cancel, then it's equals to W over root 3. The story is difficult, so different, but the way and the answers are same. Story, the previous question and second and third question actually is just the same, but that's different stories. Is it okay? We'll go to another question then, right? Can I erase the board? Right, a uniform rod PQ of length 7 meters. Uniform rod PQ of length 7 meters and mass 12 kilogram is pivoted at the point capital R. Where PR equals 2.5 meter. Where PR is 2.5 meter. Yeah, PR is 2.5 meter. Calculate the mass of the particle. Calculate mass of a particle that must be attached at capital P, that must be attached at capital P to maintain the rod in a horizontal position. Maintain a rod in a horizontal position. And also find the normal reaction acting, and also find the reaction on the pivot input. Reaction on the pivot input. This is a pivot. It's a knife edge is placed there, and we balance the rod is. So it is a uniform rod. The length of 7 meters. This is at the 2.5 meters. Tell me the answer then. Calculate and tell. So if there should be some particles attached there to make it in equilibrium. What's the mass of this? All right, that's a 4.8 kilogram reaction, and right, it's 4.8 kilogram. Let's see. I think it's correct. Let's say it is mg, the weight is there, and then the weight of this rod is there, that is 2 kilograms, 120 Newton. And our reaction, let's consider this R is there, so I'll use a different name later as N, let's say normal reaction. So this is at the 3.5 meters, right? So then it should be 1 millimeter. Yeah. So that means that if you are taken the moment about the R, because it is in equilibrium, this moment about any point should equal to 0. So then mg multiplied by the distance 2.5, that should equals to the, that's clockwise moment. C equals to anti-clockwise, 120 multiplied by 1 meter. So G is 10. So M then equals G 10, you can cancel. And this 12 divided by 2.5, no? That's 4 and 2, 6.8. Yes, your answer is correct. And then overreaction, the total upward forces that equals to the total downward forces, the 120 plus the 48, then 168 Newton. So our that's a result and net force should equals to 0. Yeah. So that's the way you can write. You can take the moments about any point make and it's equal to 0, and the resultant force acted on any direction also can be 0 when it is in equilibrium. Okay, I'll erase this one. Then with another question, it's considered like this. You think as you have a picture with the frame, right? That's mass of this picture frame is 4 kilogram, right? And you plan to hang it on the vertical wall by putting by a string which attached to the 2 points on the frame to a nail on the wall, right? So symmetrically you need to do it, right? But this string has the breaking stress, this breaking tension of the string is 2.5 kilogram. That means that 2.5, more than 2.5 kilogram, it cannot be hung. If the tension is over that 2.5 kilogram, so it's breakdown. The distance between these 2 points, 60 centimeters. Okay. To hang this picture, what should be the minimum length of the string you have? Okay, you can write the question. A picture with a frame of mass 4 kilogram is planned to hang as shown in the figure. Is planned to hang as shown in the figure. Shown in the figure by means of a string. By means of a string with string of a breaking tension of 2.5 kilogram. The string of breaking tension 2.5 kilogram. The distance between the points P and Q is 60 centimeters. The distance between the point P and Q is 60 centimeters. And the picture is hung symmetrically. Should be symmetrical. Symmetrical. So what is the minimum length of the string required? What is the minimum length of the string required? How rather weights mass forces acting on it. So its weight is 40 Newton. That's tension of the string. That's T. I'll take this length as this side is LO2 and other side is LO2. The total length is L, the string, right? Then this, if it is symmetrically right, this force is also passes through the line. So you can write in the tension in these directions. This point you can consider that's yeah, taking the forces acting on this picture frame. The upward direction you can write as 2t. This angle is theta, let's say. That's cos theta. It is t cos theta from this side and t cos theta from the other side. 2t cos theta, that's equals to mg, the weight of the picture frame, right? It's 2t cos theta Since I'm writing the cos theta, that's equal to mg divided by 2t. And for minimum length, minimum L, go into this for the breaking, right? So if this tension, that's a minimum, maximum tension is this 22.5, that 25 Newton. This is the maximum tension. This is after this tension is break. So maximum tension means that's the minimum value of the cos theta, then, right? So if I suppose this minimum value of cos theta, that's equals to the mg is 40 and 2 into the maximum value of the tension is 25. Then you can, because we can write, if you know, for maximum T max is gives the minimum cos theta. So that's equals to 4/5. Right. So then choose in this triangle. You can write in sine theta. Sine theta, that's equals to the 60, half of 60 is 30 centimeters, divide by L over 2. So that is then 60 over L. So cos theta, you know that. You draw the triangle like this, theta is there, cos theta is this 4/5. And then if it is 4 and 5 with the hypotenuse, this should be, or the opposite side should be the 3. Then sine theta, if the cos theta is minimum, the sine theta should be maximum, because they have a reciprocal relation. If sine theta increases, cos theta decreases, like that. So then this should be the maximum sine theta. So it is 3/5 for this case. So if the sine theta maximum means that the length should be the minimum. That's how you can find the length, minimum length. So minimum length is equals to the if it is simplified, this is 20 divided by 100 centimeters. So that is 1 meter of length you require. Is it clear you to this? Understand? If I want to explain it, tell me again. Okay, great. Now, okay, then I'll stop the class from this point, because that's generally also said, told me that he sent a message and he want to leave because he go to church or something. So next week we'll discuss the other part. So there's some questions and then we can start the work in energy and power. So there's theory regarding this equilibrium. It's all finished, but some applications we need to discuss. And one of the experiment under this we have to explain, that is how you can find the mass of an object using a principle of moment. So that's how the beam balances are working. We have to discuss. So I will show you that how to do it. You can get a ruler and then hang the masses, and then you can change the distances. So I will send you the practical guide and also the structured DC type questions related to that. So we'll discuss also. Okay. If you have any doubts and questions, you can ask. If not, we'll stop the class. Then do the class in action. God bless and good night.